Well, good morning, everyone. It's a morning for me here. So this talk is about the work we've been doing on finite element methods, foundational finite element libraries, and work with applications in the Livermore lab in the US, as well as in this co-design center that is part of the Exascale computing project, again in the United States. And I must say, this is the work of large teams of people. I'm just presenting the work. A lot of folks are involved. And if you're interested, please follow on, visit our website, and you can see everybody that participated in making this possible. All right, so our starting position is that when it comes to large-scale simulations, and particularly multi-physics large-scale simulations, finite element methods are a very natural choice for discretization, particularly for unstructured grids, problems with complicated geometry. And that's because on continuous level, you have all these spaces that correspond to different physical quantities, like kinematics is typically something that's continuous in H1. Electric field has normal tangential component in H curl. Fluxes have have continuous normal component in H div. Thermodynamic quantities typically discontinuous in L2. So you have this sequence of spaces called the Durand complex that's very naturally connected with various differential operators. And finite elements allow you to bring this this whole environment, the spaces and the connecting operators in a very compatible way to fully discrete level. At Livermore, we've been using finite element discretizations for multi-physics simulations that involve radiation diffusion, electromagnetic diffusion, compressible hydro, and more. But as part of the Exascale computing project, we've been applying them to many, many other simulations, and we always like to work with new applications. Now, one thing that adds to that is that with new architectures, how the finite element methods are becoming increasingly important. And that's not just because they give you a good bang for your buck. It's well known that for smooth problems, that's the best way in terms of efficiency to solve them. We've shown that also for problems that have discontinuities, like compressible flow problem, like this one here shown on the right. This is a purely Lagrangian simulation with 8th order Lagrangian finite elements. And as you can see, you get benefits here, even though the global order is still first. You can push the simulation much further away in time because your geometry can bend. So this here is one computational element, and you can see some elements following the slip line. Your geometry can bend and follow the flow. And so there are benefits from a mathematical perspective, but maybe more importantly, with the new hardware we're getting, harder methods are also very beneficial from HPC perspective, because for the same amount of data stream from memory, you can do more computations essentially for free, getting better solution in the same amount of time. Now, of course, this is another example here is this inertial confinement fusion simulation that is relevant to a big laser facility we have at Livermore. Now, of course, this is not for free. Harder methods have great power, but they need to be controlled. You need to control oscillations. You need to upgrade existing methods to support description that has wide variety and variation inside an element. And so these methods require new research, but it's interesting research, and it's something that you know, from our perspective, is also a benefit because it keeps it interesting and it motivates for the mathematical development. Okay, so the Exascale program in the United States recognized the importance of how the finite elements, and as part of the Exascale computing project, one of the so-called co-design centers was specifically formed to develop how the finite element methods on general unstructured grids without any restrictions on the order, including, of course, curved geometry, curved meshes, and structured adaptive mesh refinement for a variety of applications. And that's the Center for Efficient Exascale Discretization, or SEED, that was mentioned earlier, that I lead. It involves quite a few people, about 30 researchers from 2 labs and 5 different universities. And the goal of this center is really to make these methods as performant as possible on exascale platforms, working very closely with the vendors, and then deliver them to applications in library form, in which they can easily incorporate them in their simulations and take advantage of all the optimizations from one central place. So they don't need, you don't need to reinvent the wheel in each separate application. Okay, so the 2 main delivery mechanisms, the 2 main libraries that we have in SEED are the NEC 5000 code that is been developed at Argonne National Lab, and the MFM Finite Element Library that is developed at Livermore. Both of these have had recent versions that are GPU capable. As you probably know, all the exascale supercomputers at the United States will be will have GPU acceleration, and so porting to GPUs is a very critical, has been a very critical focus for us. And for NEC 5000, the GPU version is called NEC RS, and for MFM, that was just part of a regular release as of 4.0, and which was about 1.5 years ago. MFM supported GPU acceleration, and the latest release 4.2 came maybe about 3 months ago. All right, so in this talk, most of the results I'm going to present will be from MFM, and I just wanted to give a quick overview here, just in case you're not familiar with MFM. This is a finite element, general purpose finite element library we've been developing for more than a decade now at Livermore. It's free, open source, lightweight, designed to be used in a variety of applications. It has a number of combination of features that we found is particularly important for us and our customers. Number one, it's very flexible. So we treat, for example, simplex and tensor product elements of triangles and tets and quads and hexes on the same level. So we support them equally. We don't specialize in one or the other. There is a variety of bilinear and linear forms for a variety of methods, from regular Galerkin to discontinuous Galerkin, HDG, IGA. From the meshing perspective, you can do local conforming and non-conforming refinement for simplex and tensor product meshes respectively. We support quite powerful mesh optimization. That's important for some of our applications. So there's a lot of flexibility. You can quickly put together a variety of methods. Now, a main focus for us, obviously, is high order methods. And so we support arbitrary order in the whole DRAM complex, including the geometry. And that's done in a way that is extremely scalable. We have large supercomputers, so it's scalable. MFM is scalable to millions of cores, GPU accelerated, as I said, now for about 1.5 years. And it's designed also to enable development that can start on a simple laptop with a serial version, and with small amount of changes, simple serial code can then be turned into a highly scalable code, and with a bit more changes to GPU accelerated code. So it's really designed to for the full range of development platforms, from laptops to the largest exascale supercomputers. One of the maybe distinguishing characteristics of MFM is that it's very tightly integrated with Hyper and other solver libraries. For almost all of the discretization that we provide, we have very scalable solvers. For example, we provide directly AMG accelerated preconditioning for all the spaces in the DRAM complex, including H-curl, for example, which is not trivial. And we have a lot of examples. We're integrated with many other numerical packages. We're part of a variety of groups like the XSDK, OpenHPC, E4S, and so forth. And these are just some of the examples of the Howard spaces and one of our applications in topology optimization. All right. So this was one of the applications that NFM is used for, but we target many more. And in the ECP, that includes compressible flow, modeling nuclear reactors, climate, wind energy, modeling flows in urban environments, additive manufacturing, subsurface flow, combustion, and fusion. These are the ones that we have signed up for, but as I mentioned previously, we love working with applications. We love developing new methods. So if you'd like to work with us, please don't hesitate to reach out. But now I'd like to, with a background out of the way, I'd like to spend maybe the rest 10 minutes of this talk discussing how we achieve performance. What's our approach to get performance at these exascale platforms? And on a mathematical level, it starts with understanding of what finite element operators are. The way we think about them, so traditionally you would say, oh, a finite element operator is just a global sparse matrix. We assemble it, we use an iterative or direct solver, and that's it. But that's not sufficient for performance, and that's not sufficient certainly for harder methods. What is more useful is to think of a finite element operator A as a sequence of variational restrictions with kind of gather-scatter type operators. And these operators, P, G, B, they take you from a set of degrees of freedom to continuously expanding and telescoping set of degrees of freedom. So the first interpolation operator, P, takes you from the global parallel unique degrees of freedom, the one that you're solving for, to degrees of freedom on each device or on each MPI task. Okay, so this just copies data potentially. If you have adaptive mesh refinement, performs interpolation. After you apply P, you've just zoomed into one MPI task. You don't worry about parallelism anymore. The next similar operator is G. This takes you from a local mesh to the degrees of freedom on each element individually. So G allows you to zoom in to element level. The B operator, B stands for basis here, takes you from degrees of freedom on the elements to quadrature points on the elements. And at this point, at the quadrature point level, that's where all the physics is. That's where all the Jacobians of the geometry, that's where coefficients and artificial viscosity material models get evaluated. So this operator D here is really a kind of like diagonal or block diagonal, if you have something like diffusion operator that is embarrassingly parallel. It performs computations quadrature point by quadrature point. And so you go this way, you scatter all the way to the quadrature points, perform local computations, and then you start gathering. You go from quadrature points to degrees of freedom on the element, to degrees of freedom on the mesh, to degrees of freedom on the global problem. Okay. So what we like about this decomposition is that it explicitly exposes these levels of parallelisms, and it separates concerns. It separates the parallel concern, which is entirely in P, from the meshing, the topology, from the basis, and from all the geometry physics. And from our perspective, the applications really only care about what happens here at the quadrature points. Everything else is accelerated by us and provided by us in the general finite element library level. Okay. And when it comes to high order, if you want to achieve performance, you don't perform these operations and assemble a global problem. Instead, you perform everything on the fly, all the computations from here, all the way down to the quadrature level on the fly, and maybe only assemble and store data at the quadrature points. And we call this partial assembly. Okay, this is just a quick example. If you have a say, diffusion problem, the stiffness matrix, one entry of it is just this integral of the dot product of the gradients of the basis functions. If you write this as a sum over the elements, and then you apply a quadrature in each element, then the sum that you're getting here, these B operators are basically the gradients of the basis functions at quadrature points. These sums here represent G, and if you get the sum over a parallel partitioning externally, that will represent P. and everything else, everything that depends only on the quadrature point. So as you can see, the Jacobians here, the coefficient, if you had, I guess I dropped the nu here, but nu of qk will be also here. That's in the D operator. All right. And the point is that you assemble and only store this. And one other detail, if you are on tensor product elements, you don't assemble and store this B operation, the degrees of freedom to quadrature points either. Instead, you use something called sum factorization to apply it much faster. And instead of a complexity of O of P to 2D, P being the order, you get away with only O of P to the D memory transfers and O of P to D plus 1 operations, flops. So that's a significant, for higher order in 3 dimensions, that is a 3 orders of magnitude saving. And so, and these tensor contractions are essentially the same things that machine learning is optimized for. So you can take advantage of tensor cores and other machine learning specific hardware. All right, so one of the things that we have done in SEED is develop benchmarks where we can compare different higher-order codes, learn from each other, and optimize each other's code by a friendly competition. These are out there for the whole community. This is the website. We call them actually bake-off problems because we do use them for friendly bake-off competitions. And they're simple things. There are things like, you know, assemble and solve a system with the mass matrix or with the stiffness matrix with this quadrature rule. But there is a mixture of some compute intensive and nearest neighbor communication. There is a dot product, for example. It's a lot of fun if you do have a finite element code, a higher order code in particular. We would love to have you try those and submit your results. So far, we have had results from NEC, MFM, and DIL2. This is just an example of the type of plots and type of results we're getting. These plots, you'll see a lot of those here. So let me spend some time explaining this. On the x-axis, you have local problem size. So these are run on 512 nodes of BGQ with 32,000, with 32 tasks per node. And on the y-axis, you have the throughput. The throughput is degrees of freedom per second. And here we're talking, you know, about 70 million degrees of freedom per second. And we call this 70 megadovs. Different curves correspond to different orders. And as you can see, going from, you know, this is first order, going to higher and higher order pays off. This is uniformly for all the codes, from NEC 5000 to MFM to DIL2. We have a paper where we are discussing this in more detail. But one thing I just wanted to point out from this relatively old results, that when we run them first, we saw this big jump that DIL2 is much better. And we would look at that and we were like, oh, what's going on here? And it's clear actually if you check in this curve that there is some vectorization, explicit vectorization going on over the elements. We learned that. We tried that in MFM, and this we went from this to this result, and now we gotta. This is one of the benefits of this type of bake-offs. It motivates you to improve your code, and we got a code that's about twice faster. All right, so since we're gonna see quite a few of these plots, I wanted to spend some time discussing them. When you have a plot like this, and these kernels that we have are all memory bound, you have for your local problem size, you have a maximum performance you get. And that's usually what's quoted. If you're on a single GPU, that's maybe what you care about. What's the maximum performance I can get in degrees of freedom per second, depending on you know, the complexity of your algorithm. You translate this in teraflops and so forth. But that's not the whole story if you're in a parallel environment. And that's the point that I'd like to make here. If you're in a parallel environment, you're willing to run not at 100% efficiency, but maybe at 80% efficiency, but use more parallelism, right? And in that setting, the time to solution at 80% efficiency is this number, n sub 0.8, which is the local problem size at which you are getting 80% of R max, okay, 80% of the maximum you can get, divided by 0.8 R max, right? And it turns out that if you introduce another parameter, T0, which is kind of the serial portion of your algorithm, for GPUs, that's the cost of kernel launches, for example, memory transfer. T0 and sub 0.8 and Rmax are related in this way, right? So n sub 0.8 is proportional to 4 times T0 and Rmax. Okay? So for given Rmax, if T0 is small, n sub 0.8 will be small, and if it's large, it will be large. Okay. And so here's the point. If you want, in a parallel environment, if you care about strong scaling, if you care only about weak scaling, Rmax is the only thing you care about. But if you care about strong scaling, then Rmax is not enough. If to achieve Rmax, n sub 0.8 has to be really, really large, your actual time to solution may be worse. You care about at least 2 of these 3 parameters that are related this way. And in what I'm going to discuss later, I'm going to focus on Rmax and n sub 0.8. Once you know those 2, you can kind of predict the whole curve with a simple model. This is an example. And this is the actual curve that you get. And then you can
about 5 minutes left. Yeah.
Okay. Okay. All right. So here's some quick examples. These are the results on CPU platforms, 2 different backends, and you can see that the best we get is for pretty high orders. The Rmax we're getting here is about 500 megadovs, and the n sub 0.8 in the hundreds of thousands. On GPUs, we can get much higher Rmaxes. This is about 2.5 gigadovs, but the n sub 0.8 is also much higher. Okay, and you care about the ratio of those 2. Okay, the n sub 0.8 here is in the millions. We can extend this to multiple GPUs. This is going up to 1,000 GPUs with MFEM, and the performance drops locally from 2.5 to 2.0, but still aggregate performance of 2.1 teradovs and problem size of 34 billion solved in a matter of less than a minute. This took a lot of work. I'm not going to go into the details, but there's a lot of GPU optimization that has gone in MFEM. And these kernels then were promoted all the way to the level of the library, where we can support different backends at runtime, and we can target both CPUs, GPUs, from NVIDIA, from Intel, from AMD, from the same code. These are just results on my Linux desktop, just to see what a out-of-the-box example 1 in MFEM can do with all the variety of kernels that are available now to our users. These are runtime selectable, so you build one executable and you provide exactly this as a parameter, as a device parameter during runtime. And as you can see, we have 3 sets of backends here, single core ones. So this is a single thread. And the best one here, this seed developed ones. Multi-core that use MPI or OpenMP. These are about an order of magnitude faster on this machine. This uses a 16-core Skylake CPU. But the real winners are the GPUs. This has a GV100 NVIDIA GPU. And as you can see, using these GPU backends gives you another order of magnitude improvement. And again, the best performing one here is the one from Seed. Going from first to 8th order for this problem is the same number of degrees of freedom gives you about a factor of 3. All right, we've applied this to many applications in the ACP. I don't have the time to talk to you in details about them, but one of them is Compressible Flow. This is an application at Livermore, and they've seen here speed ups compared to the CPU cluster that they've used between 12 to 13 in the different phases of the simulation. Another application is in additive manufacturing, a polycrystal plasticity mini app, where the speedups have been about 15. And also the NEC 5000 code. I focus mostly on MFEM here, but the other seed partners have also accelerated their code significantly. And so they are seeing a 4 times faster code with much smaller time step and much smaller, and much bigger NSUB 0.8 on Summit, the GPU machine that is biggest GPU machine in the United States right now, versus Mira, which is a BGQ machine. I focused a lot on the discretization and kernel optimizations, but we're doing a lot of other work related to hardware methods as part of the general hardware software ecosystem. So we do a lot of work on meshing, on structured MR, these low-level tensor contractions, quite a bit of work on solvers, especially matrix-free solvers, general interpolation, visualization, and so forth. Please visit this website if you're interested to learn more about it. And this is generally a recommendation. If you'd like to learn more, just visit our websites. They're pretty complete. This is the information for SEED and the ECP Code Design Center, and this is the information for MFM, the Finite Element Library. And I went a bit fast here at the end. I apologize for that, but that's my last slide.